Good afternoon, everybody, and welcome to this talk, which will be delivered by Rob Hughes. I am Emma Rose, Faculty Projects Manager from the Faculty's Industrial Liaison Office. If you have any questions for our speaker today, there'll be a Q&A at the end of the presentation. Please submit any questions you have to the Q&A tab found at the bottom of your Zoom screen. This talk is part of our Faculty Research Showcase event. The purpose of this week-long event is to demonstrate the breadth of research capability we have in engineering at Bristol, to provide stimulus for a conversation and hopefully future collaboration. I will now hand you over to Rob, who will talk about finding fibres, counting cracks and beating bacteria, applications in electromagnetic sensing.
Thank you very much, Emma, and thank you everyone for coming to join me today. It's my pleasure to share with you some of my research. So hopefully you can now see my screen and I'll kick off. So my name's Dr. Robert Hughes. I'm a lecturer in non-destructive testing. And today I want to share with you some of the applications that I have been working on in electromagnetic induction. As a member of modern society, we often have very high expectations for how infrastructure around us should behave. We expect bridges to remain standing. We expect the lights to stay on. We expect, more often than not, supply chains to remain open. And we expect planes to continue flying. This confidence is only possible through years of trust being built up in these industries and through these manufacturing and monitoring processes that exist around these different industries. But our confidence is so pure often, particularly when it comes to things like bridges and power stations. It is tantamount to a belief that they are almost a fundamental rule of nature, like gravity. And whenever anything does go wrong, then whole industries can grind to a halt until answers are found. This is obviously extremely costly, not only for the industries involved, but also just in public confidence. And it's for this reason that the stringent and rigorous monitoring and manufacturing processes exist in order to build that confidence and make sure that people feel safe and can continue existing in their modern society without having to worry about these infrastructure. One of the fundamental pillars of this rigorous monitoring and manufacturing process is something known as non-destructive evaluation. The techniques used in non-destructive evaluation will not be unfamiliar to anyone who has been to hospital before for a broken bone or for a pregnancy scan. We regularly use them in hospitals in order to try to find broken bones, gallstones, things like that. We use X-ray CT, we use ultrasonic inspection, and we also use thermography. Anyone who's currently had their temperature taken using a thermal thermometer, it's the same principle. And these are all techniques that can be used in industry as well to determine the quality and structural integrity of components. But we can use other techniques as well. In the center here, there's an image of something known as dye-penetrant testing, which can be used to detect defects. And on the rightmost image here, there are little images that look like owl's eyes out of the midnight blue. And these represent indications of defects as seen by an eddy current or electromagnetic inductive sensor. These techniques are used, and many others with them, in order to detect damage in materials before they can potentially cause the failure of a component. And they are used throughout the lifetime of various components within industry, from manufacture right through to its final use. And that is to ensure that nothing can possibly go wrong. I myself specialize in inductive sensing, as you might have guessed from the title of this talk. So today I'm going to talk to you about the applications that I've been working on in this non-destructive evaluation field. I typically use very, very small coils, and that's so that I can find very, very small defects, which is one of the main advantages of eddy current testing. it has this advantage over many of the other non-destructive testing techniques that it can find these very, very small sub-millimeter defects in all sorts of industrial components. The challenges that I'm currently faced with, or that the industry is currently faced with, is the use of modern materials. And by modern materials, I mean things like superalloys. Superalloys are the kinds of materials that make up components in some of the most extreme environments in industry. In the top left there's an image of an aerospace jet engine, and right at the very center of that image here, there will be components that operate at such high pressure and high temperature that if they were to fail, the failure would cause the total failure of the engine. So we cannot allow any kind of damage to propagate within these materials. As such, the strictest tolerances are applied to these components. The problem that we are faced with in the industry, and eddy current inspections are regularly performed on these types of materials, is that the superalloys used in the heart of these jet engines often have unfavorable material properties for inspection. They might have high levels of background noise, which means that defects could be obscured by noise in the background that cannot be removed because of the material properties. As you can see here, there's an image of a number of different defects in a aerospace superalloy, and you can see only really just about defects C and D, and this is what a typical eddy current inspection might look like for these kind of materials. So much of the work that I've done over the previous years has been looking at ways of enhancing the sensitivity of these eddy current techniques on these difficult to inspect materials. One of the techniques that I've developed has been using a resonance-based technique in order to tease out the defect signals from the surrounding background material noise, allowing us to actually detect the damage with a higher signal to noise and a higher confidence. This then allows designers, modelers, and manufacturers a greater confidence in their components that they are making, and allows them to more accurately predict the lifetime of these components. Something that I've been doing in more recent years has been looking into the characterization of defects. So using eddy current inspection data and these inductive measurements in order to determine the absolute depth and the extent of damage within certain materials. The idea being that if you're able to more accurately size your defect, then you are more accurately able to determine how long it will last in its mechanical environment. So this is some of the more recent research that I've been doing. But there's another problem. I've spoken a little bit about the modern materials that we use, but that's a current snapshot of what materials exist in non-destructive testing and in industry. But there's always a future. And the future of industry at the moment is looking very different to the one that we know and love. Through the use of all sorts of advances that will be the cornerstones of Industry 4.0, as it's referred to, and the advanced manufacturing techniques that come with it, there are a range of different materials, manufacturing processes, automation, and also artificial intelligence that can be used in order to redesign the components that we are so familiar with. This is an example of a generative design component. I'm not entirely sure what the component is for, but you can see this looks more organic than anything that is typically produced. These components are designed to reduce to as small a possible level as possible the weight of the components while still maintaining the tolerances to mechanical loads. But as you can see, the geometries are extremely complex. The joins between different parts are potentially very thin and very complex geometries, which makes the inspection of these regions very difficult. But the detection of defects within them is all the more important because there is very little redundancy in the material. So this is potentially one application of inductive sensing for the future that we need to look into in terms of challenges. One of the other very significant challenges that we're faced is new manufacturing methods and new materials. The image that I'm showing here is of an automated fiber placement system, which is applying carbon fibers to a complex geometry. Now, carbon fiber materials will almost certainly make up large percentages of industrial infrastructure in the future. They're already being slated for use in the aerospace industry, and things like the Boeing 787 Dreamliner will be using 50 to 80% of its fuselage made out of carbon fiber. And all of these things must go through the same stringent monitoring techniques that we currently have for aircraft. But with carbon fiber composites and with automated fiber placement machines, we're faced with a couple of challenges as non-destructive testers. We have not only complex geometries, but we also have complex materials with an almost infinite number of different designs and layups, which we have to inspect, and we have to detect new, different types of flaws that we've never seen before in typical solid materials such as metals. In recent years, I have been looking into how eddy current inspections can be used to monitor carbon fiber materials and examine the fiber orientations in different carbon fiber composites. Fortunately for us, carbon fiber is electrically conducting, which allows us to inspect them using eddy current testing. You can see here these top 3 images of different carbon fiber materials with their fiber orientations. And we're even able to use advanced data processing algorithms in order to unpack the stacking sequence of these composites. Of course, the mechanical structure of these composites is derived from the orientations and the relative orientations of these fibers. So understanding exactly what those fiber alignments are is extremely important for understanding fully the mechanical properties and also the lifetime of these components. I'm also interested in looking into the different kinds of defects that can occur, both in the manufacturing process and also during life cycle of these materials. Here's a model showing how fiber alignment or changes in fiber alignment can influence your inductive measurement. And these are the kind of defects that can be seen during the manufacturing process. And these are very, very important for us to be able to find, characterize, and quantify. I'm not only interested in the as manufactured components, but also one of the fundamental challenges with the ramp up of carbon fiber manufacturing is that you must be able to ensure that what you're laying down using your automatic inspection system is what you think you're laying down. So some of the work that I've been doing recently has been looking into inline monitoring using eddy current testing, with the idea of in the future having closed loop inspection control, which means that as soon as you monitor any kind of fluctuation in your manufacturing quality, you're able to readdress this. And as such, you'd then remove any final stage inspection and rework required, therefore increasing the amount of material, the rate of manufacture of these components, which is going to be essential for the future of manufacturing in these industries. But there's another less expected application of electromagnetic induction, which is the detection of bacteria. None of us really over the past year will be unfamiliar with rapid diagnostic testing. Hopefully, well, not hopefully, but maybe many of you have used a COVID test over the past year, and the lateral flow tests that are now available in the UK are a perfect example of what's known as point of care testing. This allows you to perform a test and get an answer in a very short space of time, giving you the confidence that you are not infectious or you are infectious and that treatment may be needed. Point of care diagnosis is also very important for bacterial infections. Bacterial infections are one of the most significant causes of infections around the world, and they are coupled with another global challenge that is facing us, which is antimicrobial resistance. This means that bacteria certain strains of bacteria are becoming resistant to certain antibiotics. And without knowing whether those bacteria are resistant, we have to determine what the most appropriate antibiotic is for that infection, so as not to perpetuate antimicrobial resistance and make it worse for the future. So one of the areas that I've been working in recently is trying to use both magnetism and inductive sensing in order to help advance these point-of-care diagnostic tools. Through a series of smaller projects and as well as a collaboration with the University of the West of England, I have been helping to develop techniques for small point-of-care diagnostic tools that can concentrate, separate, and detect bacteria using magnetic nanoparticles. Here's just a simple diagram of the approach being used. But the idea is that we could incorporate this kind of technology into small handheld devices that could go anywhere in the world and could therefore allow rapid diagnosis to happen, not in days and potentially weeks sometimes, but in a matter of minutes, thereby allowing effective treatment much quicker. This is obviously extremely important around the world, but one of the issues that is extremely important when it comes to point-of-care diagnosis is the idea of democratization, so allowing this technology to be accessible to anyone in the world. This has led to a really interesting work that I've been conducting with researchers at the University of Bristol into developing extremely low-cost 3D printed methods of developing things called microfluidic devices. These are the microfluidic environments that underpin lab-on-a-chip and point-of-care technology and allow small amounts of fluid to be manipulated around a device the size of a credit card and analyzed in the same way that samples might be passed around a lab. On the right-hand side here, there's a video of us demonstrating our 3D printed technique, generating microparticles or micro bubbles, which are regularly used in diagnostic tools. The potential for this technology is not only to democratize the prototyping of microfluidic environments, but it's also to allow anyone in the world, both education and research, more access to microfluidics, more access to lab-on-a-chip environments, and therefore hopefully invigorating the field itself, leading to more lab-on-a-chip point-of-care technology. The technique that we've developed is therefore costs a matter of fractions of a pence per device, as opposed to the pounds that it can cost to produce microfluidics typically. So the applications that I've shown you today are just a snapshot of some of the research that we're doing here at Bristol on inductive sensing. But there's hopefully, as you can see, a whole range of different applications out there, and the future of inductive sensing may well be somewhere entirely different. So if you have ideas, I'd be happy to discuss them. Thank you very much.
Many thanks, Rob. That was a very interesting, informative talk. Just a reminder to the audience today, if you do have any questions, please feel free to submit them through the Q&A panel at the bottom of your Zoom screen. Just to kick off the questions, Rob, just talking about the defects as you were at the start of the talk, at what point does a defect become a material property?
Yeah, that's an interesting question. There becomes a point when the actual structure of a material, you can get no smaller. So whenever we have a crack, it often is produced at what's known as a grain boundary. And we have these grains of material, just like grains of sand, and inside the material all squashed together. And typically that's where cracks emanate from. And we're getting to the point now where you can actually detect those grain boundaries. And a lot of the noise that we measure in those aerospace materials is those grain boundaries interacting with our sensor. So there will be a point at which we will just have to accept that the things that we're detecting are just the material properties. And it's not really far away from the sensors that we have at the moment.
Okay. What are the bigger challenges that you face when you're inspecting complex structures?
So the biggest challenges really are eddy current inspection, or inductive sensing in general, is very dependent on its proximity to the material. So this includes the height, and it also includes the its alignment with the surface of the material. So as we go over varying geometries and different surfaces, the eddy current interaction therefore experiences these feature dependent signals. So part of the work that I'm hoping to do in the future is looking at how to remove a lot of those geometric effects from the signals, so that we are only ever seeing defects. And that's really the major challenge that I see in the future.
Mm-hmm. Great, thank you. And moving on to the bacteria sensing technology that you talked about towards the end of your talk, how do you see that technology evolving?
That's another great question. So the technology at the moment is using fairly advanced sensors that are fairly expensive to manufacture, but that's only the case because they are prototypes at this stage. My overall aim for the research that I'm involved in is to try to reduce the cost of those things. Obviously, rigor and the quality of the inspection, as I'm calling it, or the quality of the diagnosis, is the most important thing. But realistically, the most interesting and potentially impactful applications are in parts of the world where there isn't enough resources in order to support very expensive machines in order to do these diagnoses. So producing low-cost versions of them is one of the major challenges that I would like to evolve.
Great, thank you. I guess as a follow-on from that, just looking at all the different projects that you're working in generally, how do you see them, or where would you like them to be in the next 5 years? How do you sort of see them moving over the next 5 years or so?
So I would, there's a couple of things really. So in terms of the crack detection and enhancement, I would love to develop that into genuine sort of sensors that can be used in industry. At the moment, it's still a lab-based technique, so I'm talking with manufacturers at the moment to try to incorporate them into sensors, so that they can actually start to enhance the sensitivity. And in terms of the inline sensing, which I think is where the future of eddy current and inductive sensing is going, is building those systems into the automated process. So for all these robotic placement systems that are applying carbon fiber to complex geometries, incorporating these sensors into a sort of closed loop monitoring, I think is the exciting part of it, really.
Brilliant. Thank you.
I'll talk as well about the bacteria, but
yeah.
yeah, and the bacteria sensing, really, I would love to have developed some low-cost techniques, and also I'm keen to expand this out as well to for outreach and getting schools and students, young students, involved in learning about lab-on-a-chip technology and testing. It's something that I've been exposed to as an engineer, which I find really fascinating, and it's a very multidisciplinary research area that's very exciting, I think.
Great. You touched a little bit on your existing involvement with industry, and you're taking some of your research there now already. Is there any sort of anything you'd like to elaborate on there? Is there any further way that you feel like you could use, or industry could use your research that you've yet to sort of be able to tap into?
Well, actually, I feel very lucky with the number of industrial contexts that I have in terms of these techniques, and often the pull is coming from their desires to have better, more quantitative analysis of their processes. I think always with NDT, we find ourselves reacting often to the way in which manufacturing is changing so much that there's almost always a desire there before there's the the solution, which is great in many ways in that it gives us these challenging problems to solve. But it's hard for us to say you should apply this to your particular solution. But one of the advantages of inductive sensing is that it's extremely versatile. The many shapes and sizes and dimensions and things that you can use are nearly limitless in terms of combinations. So it's very adaptable to different applications and environments.
Brilliant, thank you. If there's no other further questions from the audience, I will bring this session to a close. I'd like to thank you for attending today and for your questions. Thanks also to our speaker, Rob Hughes. In the current climate, online is the only way we can really do this, and we appreciate it's not as interactive as we'd like and we're used to. However, if what you've heard today or throughout the week has captured your interest, please do get in touch with us. Our Industrial Liaison Office is here to contact you to our academics and students, and contact details will be sent after the event. Many thanks once again, and goodbye.